Hello, dear viewers. Welcome, everyone. My name is Ankita Ingole. I am a PG student from Vidyabharati College, Amravati, and today I am here to present a seminar related to the mathematics. And my seminar topic is Bernoulli's equation and its real life application. So let's see. Well, here are my contents. Firstly, I will give a little intro about Bernoulli's principle. Then we will see his history. Then what exactly the Bernoulli's principle is, Bernoulli's equation, then the equation with derivation, and the last and interesting one, its real life application. So let's start. We will start with introduction. Well, Bernoulli's principle is one of the most important results in the study of fluid dynamics related to the speed of the fluid flow to the fluid pressure. This might this might not seem particularly important, but as a huge range of phenomena, it helps to explain. A simple rule can reveal a lot about the behavior of a system. Well, fluid dynamics is a study of moving fluid, and so it makes sense that the principle and its accompanying equation, that is Bernoulli's equation, come up quite regularly in this field. Learning about this principle, the equation can describe it, and some examples of Bernoulli's principle in action prepares us for many problems which we will see further in fluid dynamics. So moving towards the history, a Swiss mathematician and a physicist, Daniel Bernoulli, was one of the first scientists to propose what is known as kinetic theory of gas, like all matter composed of tiny molecules in constant motion. In the 1730s, he conducted experiments. Then later, he published the result of his work in hydrodynamica in 1738, but did not present his ideas or their implications clearly. Later, his friend, a German mathematician, Leonhard Euler, generalized his finding in the statement known today as Bernoulli's principle. Now we see what the Bernoulli's principles say. Well, according to the Bernoulli's principle, increase in the speed of the fluid occurs simultaneously with a decrease in the pressure or a decrease in the fluid potential energy. Well, in other words, in a horizontal pipe, a highest fluid pressure is the section where the flow speed is lowest, and the lowest pressure is a section where the flow speed is the biggest. Now, we will see the Bernoulli's equation. If a section of a pipe is as shown above, then the Bernoulli's equation is written as this, where P is the static pressure of fluid at the cross section, rho is the density, g is the acceleration due to gravity, v is the mean velocity of the fluid, and h is the evolution head of a center of a cross section with respect to a datum. Now we see its derivation. It's very simple. For this, we have to consider a pipe with varying diameter and height through which an incompressible fluid is flowing. Then the relation between of the area of cross section A, the flow speed V, height from the ground Y, and the pressure P at two different points 1 and 2 is given in the figure. Now, first of all, we have to assume two conditions. The first one is the density of the incompressible fluid remains constant at both points. The second is the energy of the fluid is conserved as there are no viscous forces in the fluid. Therefore, the work done on the fluid is given as dW equals to F1 dx1 minus F2 dx2. After solving this, we get dW equals to P1 minus P2 dV. Well, we know that the work done on the fluid was due to the conservation of gravitational force and change in kinetic energy. Then the change in kinetic energy of the fluid is given as dk equals to 1 half m2 v2 square minus 1 half m1 v1 square, which can be written as 1 half rho dv v2 square minus v1 square. And the change in potential energy is given as du equals to mgy2 minus mgy1, which is 1 half rho dvg v2 minus y2 minus phi1. Therefore, the energy equation is given as dw equals to dk plus du. As we know that the work done is equals to kinetic energy plus potential energy. Well, after substituting the values of dw, dk and du, we get the equation, and rearranging this equation, we get the Bernoulli's equation. Well, this is a simple derivation of the Bernoulli's equation. Now moving further. Now this was the interesting part, real life applications of Bernoulli's equation. Well, do you ever wonder about This Bernoulli's equation is used in medical field. Yes. So let's see the phenomena of blood flow and heart attack follows Bernoulli's principle. Sound interesting? Well, we see how the problem of a heart attack occur due to the constriction in the arteries, and the constriction in arteries is due to the accumulation of plaque inside the arteries, and the accumulation of the plaque is due to the cholesterol. Then due to the constriction, the diameter of the arteries reduces, and thus the blood flow rate in the arteries also decreases. Then this decrease in blood flow rate can be understood with the help of continuity equation. But the requirement of the blood in the body remains the same, and to fulfill its velocity of the blood in the region of constriction increases. The increase in velocity at the constriction decreases the pressure inside the heart. Well, this whole phenomena can be understood by Bernoulli's theorem. Here Z is constant as velocity increases and pressure decreases. Therefore, the artery can collapse due to the external pressure. Further, to open the artery, the heart will apply the force to constrict passage of the artery. Again, the velocity will increase and the pressure inside the heart will decrease. And the artery can collapse due to external pressure. As the artery will collapse, a person can die due to heart attack. Now, moving towards the next example. Well, have you ever wondered about how aeroplanes fly? Well, it's due to the Bernoulli's principle. So let's see how. Airfoil or a lift on aircraft wings is based on Bernoulli's principle. Well, the lifting of airfoil. Well, here airfoil is a wing of aircraft. We will see in the figure number 2. As airfoil moves against the air, the above and beneath the airfoil has to cover different distances. The air flows above the airfoil has to cover less distance as compared to the airfoil beneath the airfoil. Thus, the velocity of the air flows above the airfoil increases as compared to the air flows beneath the airfoil. Well, the increase in the velocity above the airfoil will cause the crowding of streamlines above it. And the decrease in velocity beneath the airfoil will cause the rear streamlines beneath it. The increase in the velocity above the airfoil decreases the pressure in the region, and the decrease in the velocity beneath the airfoil increases the pressure beneath it. Due to this, a pressure difference is created that produces lift on the airfoil as moves in air, known as lift of the airfoil. This is how aeroplanes fly. Well, the third example is the dynamic lift can also be seen in the cricket or a baseball. Well, a dynamic lift due to the spinning of the ball is known as Magnus effect and also works on the Bernoulli's principle. As a cricketer means a bowler balls to a batsman, the spinning of a ball drags air with it. The rough ball drags more air as compared to the smooth ball. This is the reason for the rough surface of the baseball and cricket ball. The spinning ball moves forward and the air moves backward. The relative velocity of the air above the ball increases and the relative velocity between the ball and the air below the ball decreases. This effect the streamline above the ball get crowded and rear filled below the ball. Therefore, the pressure above the ball is reduced and the pressure below the ball is increased. This pressure difference is created above and below the balls produces a net upward thrust of the force. The upward thrust on the ball will cause the lift of the ball known as Magnus effect. Well, there are many more applications of Bernoulli's principle such as blowing of roofs during windstorm, Bunsen burner, designs of carburetors, of automobiles, filter pumps, automizers and sprayers. Well, this is about the applications. So here are my references. Thanks for watching. Thank you.